Okay, hello everyone, this is Pat McCauley, and today we'll be talking about pressure prisms on curved surfaces. So as you can see here, we have this problem set up. It is a water tank with this quarter circle portion, and the goal is to determine the vertical and horizontal forces of the water on section CD. So as you can see here, we have a radius of 4 feet and a height of 16 feet. And as I said, there's water in this tank. So first step is to set up the free body diagram. So what I did is I cut out this quarter circle and analyzed the forces that act on that quarter circle. So as you can see, we have F2, which is the force of the water acting on this side of the section here, and F1 is the force of the water acting on this bottom portion of the quarter circle. FH is the horizontal force of the tank wall pushing on that water to contain it, and FV is the vertical force of the tank wall trying to contain that water. And we also have the weight that we have to account for, the quarter circle section. So step 2 would be to sum the forces in the X and Y, and by doing that we would have FH equal to F2 and FV equal to F1 minus W. So now we just have to calculate those forces. Starting with F2, which is this side of the water pressure here, we'll use the equation gamma W times HC times A. And the area in this, the area in which we're referring to is this cross-sectional area right here. You don't want to get it confused with the area of the surface here, because we're talking about the area that F2 is acting on, which is the side right here. So by doing this, we have 62.4 pounds per foot cubed times 12 plus 2 feet, and where that comes from is we have 12 feet up to this point, and then we want the center of pressure for this section, which would be 2 feet down the quarter circle. So that's where the 14 feet comes from, and then multiplied by the area, which is since the radius is 4 and it's given that the length of the wall is 5 feet, it's just 4 times 5 feet. Plugging that into your calculator, you should get F2 being equal to 17.472 kips. Moving on to F1, which is the force of the bottom portion of the quarter circle. Same process. So we have gamma W times HC times A. Only difference here is that HC will be equal to the height of the tank overall. So with that, you have 62.4 pounds per cubic foot times 16 times the area, and with that you have 19.968 kips. And one of the things that confused me during class was why the height was 16 feet, and that's just because the this side of the surface, it's all 16 feet deep, so the center of this portion here would still be 16 feet deep since it's laying on its side. So hopefully that clears some confusion up with you guys. Lastly, we have to calculate the weight of the water that's contained in that quarter circle section, and to do that we just multiply the specific weight of water times the volume of that section. So the way I did this is you calculate the cross-sectional area of the quarter circle, which would be 1/4 pi times the radius squared, and then you just multiply it by the length of the section, which is 5 feet. So by doing that, you would get 3.92 kips. So we're pretty much done with this problem. All we have to do is plug in our results from calculating F1, F2, and W, and plugging that back into our equilibrium equations. So by doing that, we have FH equal to F2, so that just means FH is equal to that 19.968 kips that we calculated from F2. And FV, which is equal to F1 minus W, is simply equal to the 17.472 kips calculated from F1 minus the weight, the 3.921 kips, and that equals 13.551 kips. So, in conclusion, along section CD, the vertical force of the wall pushing on the water is 13.551 kips, and the horizontal force pushing on that water is 19.968 kips. I hope this cleared up any confusion that you guys may have had with curved surfaces, and thank you for your time. Bye-bye.